100 years ago, the French aristocrat and a very fine physicist wrote a series of 5 papers proposing a hypothesis which, according to Einstein, shed a faint glimmer of hope on the confusion, contradictions, and enigmas plaguing our understanding of the microscopic world. We shall term the hypothesis the wave particle duality. It is a central dilemma in modern physics. The hypothesis, to say the least, is startling. It seems to say that a moving piece of iron ball is, well, a wave. It is hard to wrap your mind around the idea that a solid log of falling wood is at the same time a fuzzy wave, the self-same entity, both tangible and intangible. Before we continue, we remind ourselves that the distance between the two maxima of a wave, or equivalently the two minima, is called the wavelength and is denoted by the Greek letter lambda. De Broglie was motivated to make this hypothesis partly because of a similar situation concerning light. It was well known that light is a wave. What you see on the left is the interference of two waves produced by two stones which are dropped at nearby points on a still pond. You see these crests which are equally spaced, 1, 2, 3, 4, and you see the lines which are equiangularly spaced. So there is the fact that light interfere or diffract, and there is an occurrence of integers. It was also discovered in the early part of the last century that light has a particle character. It was noticed that when you shine light on a solid metal, you knock out electrons. And Einstein explained it by saying that when light interacts with matter, it behaves as a particle, now called a photon, with a well-defined momentum and energy. And there is a relation between the two. The particle character of light, which is designated by its momentum p, is related to its wave character, designated by lambda, and the relationship is inverse, and it's joined together. The proportionality constant is called the Planck's constant, a number which is very, very tiny, 0.000330 zeros times 6. It is perhaps this notion of symmetry that de Broglie had in mind when he proposed that matter too, like light, has a dual character. Okay. So here you have on the left hand side an intangible entity like a wave characterized by wavelength, and it is related to the inverse of the solid particle's property, the momentum. Surprise of surprises, this formula, which is a centerpiece of modern physics, is not to be found in any of the 5 papers of de Broglie that he wrote in 1923 and 1924. It is buried deep in an obscure position in chapter 7 of the great master's PhD thesis, and it resurfaces 6 years later in his Nobel lecture. De Broglie contended that his hypothesis is supported by observations of the microscopic world. The hydrogen spectra had been well studied by then. It was found that these lines in the hydrogen atom have energies which are given by integers. So these N1 and N2 are integers. And just as for classical water waves, the only place where integers are to be found is in wave phenomena. Hence, my microscopic world has particles, and these particles have a wave character. Then why don't we see these waves explicitly in our everyday world? Consider a fast bowler who is hurtling the ball at say 100 miles per second, that's 160 kilometers per hour, at the batsman. What is its lambda? If you do the calculation as per the formula, the wavelength is 0.000310 zeros times 1 centimeter. That is too tiny to observe. Conversely, if you demand that the wavelength be an observable 1 centimeter or something, then if you calculate the speed, that is once again, because of the fact that the Planck's constant is so tiny, this velocity will turn out to be 0.000 and another 30 zeros times 1 centimeters per second. Very small velocity and you won't observe it. It's almost still. Experimental confirmation was soon to come, and this from the ultramicroscopic world of electrons. The electron has a mass which is about as tiny as that of the Planck's constant in appropriate units. And what two physicists, Davidson and Germer, in Bell Laboratories, US, did was they gave the electron a speed and they smashed it into the nickel atom, and the wavelength is still tiny, but it's about of the order of the distance between the two atoms of nickel. But since the wavelength is of the same order as the nickel-nickel distance, they could observe it as a diffraction pattern. A similar observation in England was made by G.P. Thomson. Both Thomson and Davison got the Nobel Prize for this. And there is an irony to it. Thomson's father, the great Sir J.J. Thomson, discovered the electron, so he got the Nobel Prize for showing that the electron is a particle. The son, on the other hand, got it for showing that the electron is a wave. And there you have it, father and son duality. So the formula is very useful. Lambda, the wavelength, is equal to h times the momentum. And knowing this formula is sufficient for the experimental biologist to understand the results of his electron microscope. Okay. There the wavelength of the electron is small and it can probe subcellular structures, or for a solid state physicist to understand crystal structure, and this they do not with electrons but sometimes with neutrons, another tiny particle, or for the biochemist to understand the structure of life, and for the engineer, the modern electronic engineer, to understand submicron nanostructures. So the de Broglie formula is enormously successful in the modern world. What should not be forgotten is that it is also the basis on which quantum mechanics was built. The de Broglie hypothesis provided a bridge. It explained the old quantum theory, it explained the Bohr theory for the hydrogen spectra, and it provided a kickstart for the new quantum theory. The story goes that when Schrödinger was asked, on Peter Debaye's insistence, to give a talk to his group on the de Broglie hypothesis, he started thinking that if the particle is a wave, then what is the equation? And there you had the famous Schrödinger equation of quantum mechanics, equivalently the matrix formalism of Werner Heisenberg. Now let us hear a few words from the great master himself.
Loi connue, déterminer, calculer, si vous voulez, la trajectoire des particules, tandis qu'après l'introduction de la mécanique ondulatoire, c'est à partir de la propagation de l'onde que la trajectoire des particules se trouvait déterminée, de telle sorte que certaines apparences ondulatoires apparaissaient même dans le cas des particules.
That is Prince Louis de Broglie at the age of 75. He lived up to the ripe old age of 95. His hypothesis was very successful experimentally, theoretically, and has enormous engineering potential, and to realize these potentials. Still, it left many in the community with a sense of unease. Einstein first supported de Broglie, but later became a critique of its ramifications, and so was Schrödinger. The confusion was so enormous that William Bragg was led to say that physicists use the wave theory on Mondays, Wednesdays, and Fridays, and the particle theory on Tuesdays and Thursdays. And on Sundays, it's up for a toss. Now, let me throw something else at you. Consider a billiard table with two identical balls, and these balls collide and then they separate. With your naked eye, you can make out which ball, one, went where and two, went somewhere else. But if these balls were waves, then during the collision, they are all mixed up, and then you don't know which one is number one and which one is number two. So you cannot identify them. So, in other words, in the quantum world, identical particles are indistinguishable. The skepticism was not confined to Einstein and Schrödinger alone. Niels Bohr, who was the patron saint of the new quantum theory, was beset with internal contradictions and conflicts. He struggled with it and turned to Eastern philosophy, where opposing principles are more acceptable. And this is his grave, and I was there 10 years ago. And right next to the grave, there's a symbol. That's an Oriental symbol, the symbol of yin and yang, what we in India would call Ida and Pingala. It is the yin, one symbol merging seamlessly into the other. So the symbol of the yin merging fluidly with the yang and vice versa is a good metaphor, but whether it explains or throws any light on the central dilemma in physics is another matter. That is open to debate. On the left, you'll find references to de Broglie's work and other useful references. I am Vijay Singh. You may look at my YouTube site for similar videos, and my email is right there, physicssutra@gmail.com. My collaborator was Vibhu Pandya. You can write to him or to me if you have questions or comments. Thank you very much.